One last topic I want to cover with regard to motion and energy is this idea of power. So power is related to work. Basically, you take the work that was performed and you divide it by the time over which it was performed. So, and that gives you power. So, in other words, as you decrease time, decrease means that you're doing the amount of work, the same amount of work in shorter and shorter time. Notice that you're dividing by a smaller number. If you decrease time, that will increase power. And notice that if you increase work, that also will increase power. Notice that if you increase time, let yourself kind of go and take your time to perform that work. Notice you're dividing by a larger number, and so if you increase time, that is going to decrease your power. And notice you can decrease power by decreasing the amount of work that's done. Okay. Sorry. So units of power are units of, is the capital letter W for watts. This is, I think somebody dropped the ball here. So units of watts, I just think W is so much like work, okay, but you can, I don't know if you can kind of tell, we usually use an italics there for the variable work, and here the watt is just a non-italicized. But you can find out what basic units a watt is if you look at what's being divided. So power is in terms of watts, capital W. So work is joules and time is seconds. So joules per second is a watt. And we can actually break down a joule and make it kilogram meters squared per second squared. And then bring in that second. Okay, so now if we kind of simplify this, we actually can combine these seconds, so we get kilograms meters squared per seconds cubed. That's a cube right there. So power. So let's do a problem. So we talked about how you calculate work. We talked about two works. In this case, we're going back to basically an object relocated from position A to position B, horizontally, and over distance D with applied force F. And we said that in that case, the work that is accomplished is equal to the force that's applied times the distance over which it's applied. So now we can actually then take that work and plug it into right here, and this just divide by the time. So we have force, we have distance, and we have time. Okay, so let me back up. So let's go ahead and work this. I think I'm going to go ahead and break it out. So work is equal to force times distance. The force is 4.5 newtons times a distance of 0.343 meters. 4.5 times 0.343. I'm going to go ahead and round it right to the answer, because notice I've got 2 digits here and I've got 3 digits here, but I can't go with 3, I have to go with the fewest. So round to 2 digits, I have 1.5, and units would be Newton meters or joules, units of work. So now I need to go ahead and knock out power. So power is work divided by time, so I'm just going to go ahead and say power equals work that I found, 1.5 joules, divided by time, which is 34 seconds. Divided by 34. I'm going to have to round it to 2 digits again, and I got 0.4. I got 0.045. And units of powers, we said, are watts. That's it. Not too bad. So let's go ahead and work this together. What if the force and the distance remain the same? So that means my work term is the same, which is 1.5 joules. I'm going to go ahead and still relocate. I'm going to push with a force of 4.5 newtons over a distance of 0.343 meters, and we got 1.5 joules. But now I'm going to go ahead and calculate my power is equal to work divided by time. My time is different here. So my work was 1.5 joules, and my new time, instead of 34 seconds, it is 17 seconds. And you get, oh goodness, okay, divided by 17. Okay, so instead of 0.045 watts, I got 0.088 watts. Seems like it should be right at twice the amount. Okay, well that's close enough. I think it's from rounding. So notice that in half the time we basically doubled the power.